Good morning, everyone. I have yet another talk on tabular synthetic data. This is a joint work with Sam, who just finished his PhD and is at a startup now, and Graham, who's at Oxford, and Will, who's my manager. I'm going to be talking about tabular synthetic data and specifically focusing on the problem of like what happens when your data sets are really wide. And what I mean by that is often all of these benchmarking papers, they talk about data sets that may have at most, let's say, 50 or 60 columns. And what we are really looking at is what happens when you end up at 100 columns or 200 columns or even 1,000 columns, right? So that's overall like a summary of what the talk is going to be about. And this is, again, like a quick outline. I'll spend a couple of minutes on a synthetic data primer, which I think is not very needed at this point. And then I'll quickly jump on to the key challenges, what were some of our observations, and a couple of innovations that we have done to address this problem. Okay. So I have a QR code here. This is for a synthetic data tutorial we ran at Gade last year, which is a very comprehensive survey on synthetic data. I would recommend and encourage people to go through that. But a very, very quick summary of why we need synthetic data is that there's a whole bunch of data sources that are extremely sensitive, and you're not allowed to use or share them without any additional protection, right? And the flip side of this is that these data sources are also often extremely valuable. They can be used for improving service quality, providing relevant recommendation. Advertising is another key application area where these data sources are relevant. And what we are proposing is that if you were to generate differentially private synthetic data, you will have this ability to access this data and use it for your downstream applications. And the key challenges here are how do you ensure these two things, right? You want to make sure that the synthetic data is a good replacement for your original data, and you want to, at the same time, ensure that the synthetic data itself does not leak any information, sensitive information about individuals, right? These are two sort of like opposing things that tug at each other. And in this talk, I'll talk about like how do we solve these problems and how do we do that for large-scale data sets. Okay. So for differentially private synthetic data, the two key things we focus on are how do we ensure that the synthetic data has high statistical similarity and enables utility for downstream use cases, right? What this means is once the synthetic data is generated, you're going to run analytics on top of it, you're going to train machine learning models on top of it, you want to ensure that the models are useful, your analysis is useful, right? That's the quality aspect of it. And the second part is privacy guarantee. You want to ensure that there's some sort of provable differential privacy guarantee that can be attached to the synthetic data so that you may use it without any further worry, right? And one key thing to note here is I'm going to introduce the AIM algorithm, which Mihail also talked about a little bit. I'll introduce it because it's sort of the current state of the art, right? It essentially follows this very simple paradigm, right? You have a tabular data set. In order to learn from this data set, often measuring low-order marginals or histograms is sufficient. That's sort of like the key insight. If you can measure a lot of low-order histograms, then you can stitch them together using these probabilistic graphical models that will give you synthetic data, right? And AIM is not the only paper to do this. There's probably 10 or 15 other algorithms that were developed over the course of last 15 years that sort of like build on top of each other, right? And AIM, which came out in about 2022, is sort of like the one that's doing the best right now. right? So the algorithm is super simple. It says first you identify which marginals you want to measure. So you do that by looking at the model that you have, which at the start might be just a random thing, and then you identify which histograms are not correctly modeled. You measure those, you add some DP noise on top, and then once you have this noisy marginal, you train the model, right? It's sort of similar to how traditional machine learning works, right? So that's the AIM paper, and this is sort of like a baseline that we'll always compare against, and will sort of show how we innovate on top of this, right? So there are two key things, two challenges, two observations that are that I would like you to think about, right? So a lot of these DP synthetic data algorithms, including AIM, they become computationally intractable when you're dealing with wide data sets or high dimensional data sets. So as you increase the number of columns to 100, 200, or 1,000, these things become extremely expensive. And one of the things that we worked on was to use generator neural networks instead of the graphical models, and sort of show how that help you scale up synthetic data generation to these wide data sets, right? So that's the first part of it. All of this work is out there on either archive reports or papers. I'll share a link at the end, right? The second key observation to think about is that a lot of these data sets are not fully private, in the sense that if you have 100 columns, there's a very good chance that about 30 or 40 of them, or even 50 of them, are like information that is either publicly available or not sensitive at all, and only the remaining part of the data is private. And in this case, you still want to sort of have this relation between public and private data in the data table, right? And what we tried is to figure out how we can explore this sort of a vertical split. So it's vertical because some of your columns are public, some of your columns are private. How do you exploit this split to efficiently use differential privacy and improve on the quality of synthetic data generation, right? This is the second part of the talk, and that's what I'll talk about next. I'm sorry, right? So the first thing is if you have AIM, which is the current state of the art, and you use generator networks and follow certain optimizations, all of which are in the paper, and I'll talk only about a couple of them here, you can address computational intractability in AIM, right? That's sort of like the summary of this slide, right? So remember in the previous slide, I had this picture where there was a graph here. This probabilistic graphical model is sort of the choke point. Constructing this graph and then training a model for this graph becomes really difficult as you increase the number of columns. And what we say, what we show in this work is that if you can replace the graphical model with a generator neural network, training this neural network is extremely easy. This is standard stuff that's been around for a while now, and it lets you scale to up to 1,000 columns very easily without too much difficulty, right? And this idea by itself is also not new. There was this paper in 2021 by Liu. They proposed this algorithm called GEM, which uses generator neural networks, but the AIM algorithm sort of beats it, and we show that there's if you add on these additional optimizations, which is an efficient privacy allocation and then disabling certain components, you can do much better, right? And I have a slide here, right? So if you look at this picture, the blue line is AIM, which is the current state of the art, and the orange line is the GEM plus algorithm that we propose. And one of the things to note here is roughly about 60 columns is where AIM sort of starts to fail. GEM plus keeps going till 120 column, which is like the highest, like the full Criteo data set. We also sort of observed this interesting thing that if you have really tiny privacy budgets, like if you have less than 0.5 epsilon as your privacy budget, this is not a good idea. Just go with AIM. When you have really noisy data, the graphical models do much better. But for a lot of realistic scenarios, your privacy budget is going to be like greater than 0.5. Typically 1, 2, 3 are the numbers that people would like to use, in which case, for all of those privacy budgets, Gem Plus sort of outperforms AIM. Right? So we show this dual benefit that you get scalability and you get better than state-of-the-art performance. So that's it. That's the result slide. I'll quickly move on to the next part of it, which is how do we adapt these algorithms when you have a vertical split, where you have public data and private data mix, right? And here we propose 3 separate strategies to sort of use the split. So first one is pre-training. Whenever you have public data in your data set, collect all of those columns separately, measure those marginals, and don't add any DP noise on top of them, right? And use these marginals to sort of pre-train your generator network. That is a very nice and intuitive way of like ensuring that public data flows through without any privacy restriction. Additionally, when these models are being trained, GemPlus measures marginals and adds noise, right? There you can have this sort of split that if you have only public columns, don't add any DP noise and correspondingly save on the privacy budget, right? That's the other key thing. And the final thing which we thought, which we found was like extremely valuable is that all of these models, they sort of generate data through some sort of sampling mechanism. So if you did conditional sampling, which is to say that keep the public data as it is, and then ask the model to generate the rest of it conditioned on this public data, you're going to do much, much better than other sort of strategies, right? So I have a slide here that sort of talks about how this works in practice. So in this picture, the blue line that you see here is essentially AIM, which is the current state of the art. And what we show is that both of these methods, conditional AIM and vertical JAM PGM, which are stuff that we worked on, sort of do better. And the improvement that you get increases as the number of public columns increases, which is also intuitive. If you have a lot of public data, your quality is going to get better, right? And sort of like the cutoff is more like if you go beyond 25% of your columns being public, then doing a lot of these things is going to be very helpful, right? We also have sort of like replicated these results on more wider data sets. So this is the income data set with like 50 columns, and we sort of see the similar result, which is that after about 40 or 50 columns, these methods start to do so much better, right? And I want to spend only the last 2 minutes to talk about a couple of applications that we found that synthetic data was really good at. So the first one being that when you do A/B test, you're essentially comparing 2 different models or 2 different changes, right? And all you really are interested in the final statistic, which is whatever metric you're looking at, what is the mean value, what is the confidence interval, right? And what we showed is that if you generate differentially private synthetic data, you can retain the correctness of these experimental results up to 95%. So what that means is for 95% of your experiments, you can, whatever result you had in the raw data is also what you see in synthetic data. And the 5% where it kind of failed are scenarios where your experiments were never stat sig. So they were like almost like there was no statistically significant result to report, and that sort of kind of flowed through. The other interesting thing we tried was using synthetic data as training data for machine learning models. So again, two sort of things that we tried. One was feature expansion, where you have certain features that are sensitive and you generate synthetic data for those and then train the machine learning model, as well as full replacement, where you just throw away the whole data and just replace it with synthetic data, right? And both of those cases sort of gave good results, where you are able to show that the model performance is what is expected. So when you do feature expansion, you get better results. When you do full replacement, you get at par model performance. With that, that was my last slide. So I have the summary slide, but feel free to ask questions.